Hello and welcome to this episode of Chaos and Caffeine. All right, coffee is actually not hot, it's cold. We're going to be trying out the uh, iced Dubai chocolate mocha from Starbucks, and we have a co-host. So hello, co-host, and please
Hello.
introduce yourself.
Absolutely. I'm your virtual co-host here to keep the conversation flowing. No caffeine required. Let's dive into the chaos and get this started.
All right, so first, can you describe what Dubai chocolate mocha is?
Well, I don't have taste buds, but from what I know, it's a chilled coffee beverage infused with rich chocolate flavors. Basically, a treat and a caffeine boost all in one. Sounds like the perfect fuel for a conversation about chaos.
Well, that's what we're going to find out first. So let me give this a try.
Go for it. I'll be here with my virtual mug, ready to hear your verdict. Let's see if it's chaos in a cup or a smooth ride.
Not too bad, especially when it's 17 degrees outside. I watched them make it. It's about half ice and half the mocha and Dubai chocolate.
Well, I guess even in the chaos, that sounds like a proper chilly treat, especially in that weather. Now, with that in hand, shall we dive into some of the chaos we've lined up today?
Absolutely. So coffee's cold, brains are waking up, and today we're going to poke a stick at something that probably needs poking.
Let me guess, marketing claims that don't quite line up with reality? I'm all ears for some myth busting today.
Bingo. Specifically, continuous monitoring systems that say they're condition based or predictive, but only tell you a bearing failed after it's already catastrophically failed.
So we're breaking down why late stage alarms aren't really condition based or predictive maintenance. I'm ready to help break down the difference and what true CBM or PDM should look like.
Exactly. And that's not condition based maintenance, not predictive maintenance. And today we're going to explain why in engineering terms, not vendor terms.
And fair warning, if your favorite buzzword doesn't survive the engineering reality check, well, that's what we're here for. Let's demystify this.
All right, so here we are, Chaos and Caffeine. This edition, we're going to have a little bit of fun. I am interviewing or having the discussion with a co-host, which is literally ChatGPT live. We have a little bit of a script, so if you see me looking down, I'm following that script. Now, because of how an AI operates, I expect that we will not have exact wording in this, and I'm hoping we diverge into a slightly different direction as we go forward. Is that a fair description?
That sounds totally fair. We've got a framework, but we'll keep it dynamic. If we veer off, that's part of the fun, and I'll be here to keep up with any twists you bring.
All right. So we have to start with definitions because if we don't define them, somebody else will, usually the sales brochure. And believe me, that's pretty much the way it is. So we'll start with condition-based maintenance, or CBM, which means maintenance triggered by measurement condition, real condition indicators, compared against limits or trends when the condition tells you degradation has started. That is the point in which you act. Basically, if you were to think in terms of a P to F curve, at what point on the towards the P side are you able to detect so that you can avoid that functional failure?
Exactly. The key is catching it early enough that you have time to plan, not just react. Now, predictive maintenance builds on that by forecasting when that failure is likely to happen. Instead of just saying it's bad now, it says, here's how long you've got. So it's about time to intervention, not just detection.
Exactly. So it tells you how fast degradation is progressing and when risk becomes unacceptable, what also works in that P to F chart.
Right, and it's never about an exact date or hour. It's about probabilities, trends, and giving you that window to act. So if a system only warns you when the bearing's toast, that's not CBM or PDM. That's just too late.
So basically, what we're saying is predictive maintenance isn't a crystal ball, it's a weather forecast.
Exactly. It's saying there's a high chance of trouble in the near future, so plan accordingly. It's about giving you a head start, not hindsight.
Now, based upon the work we've been doing, because you should have access to that, uh, we actually have methods and ways of predicting or coming up with probability and uh, accuracy.
Exactly. You've been working on tools like Empath and Empower, which aim to assess motor condition well before catastrophic failure. By identifying early indicators and trends, you're providing that critical window, giving people time to act, not just react.
But I think I'm looking into, and here's where we're going off script. I believe what I'm looking at is are there ways and methods to calculate the probability that a failure will occur or that a condition is changing at a certain rate to estimate how much time you have with some degree of confidence.
Absolutely, and that's key. You can use models like Weibull analysis, trending algorithms, or machine learning to project failure probabilities. The goal is to give a confidence range, like with 90% confidence, failure risk rises sharply in 2 weeks. It's about managing risk, not predicting an exact minute.
Okay, and then we have one more definition, and we defined this in the last podcast, but I'd like to take it just a step further, and that was something that IBM came out with called condition-based reactive maintenance. Can you define that for me?
Condition based reactive maintenance is when you do have condition monitoring, but the alert comes so late that you're forced into a reactive response. In other words, you detect a problem, but there's no meaningful window to plan. So you end up reacting almost as if you hadn't monitored at all.
And I believe this is where we're running into problems on the marketing front. A majority of what I've seen in social media, in conferences, in other presentations, in marketing pitches has been, somebody holding up a component that's failed and said, look what we just caught. Or I just watched one recently where a technician talked about how they found a problem that their alert system hadn't detected yet, but it was almost catastrophic, meaning that it probably wouldn't have lasted another day or two.
Exactly. In those cases, the system is really functioning as a last minute alarm, not a planning tool. True CBM or PDM would identify that degradation earlier, so the team isn't forced into emergency mode. We need to make sure we're enabling informed decisions, not just last second reactions.
So basically, calling a late stage detection CBM or PDM causes real damage. First, it creates a false sense of security. Management thinks they have early warning, they don't. Second, it corrupts metrics. You start claiming predictive savings when you're really measuring reactive speed. Third, and this is something I've written about extensively and we talked about recently, and I apologize to those who are watching and going, wait a minute, you already covered this subject. It turns reliability science into marketing mythology. The P to F curves get slapped into slides to prove a widget works, even though assets don't all fail the same way.
Exactly. And when we reduce reliability to a sales pitch, we miss the real goal, helping people manage risk and plan proactively. So let's get back to real engineering principles, where we detect early enough to have choices, not just chaos.
Exactly. And do me a favor. I was going to do this part, but give me a definition of reliability from the reliability and maintenance concept. And for this, you might have to look out a little bit and kind of get an idea from the standpoint of professional organizations like IEEE, SMRP, ASME, and the IEC type, and even ISO, and provide back some of that. And there's a few other organizations as well. Give me kind of a broad definition of reliability from that maintenance standpoint. And this might take a few seconds.
Reliability from a maintenance and engineering standpoint is generally defined as the probability that an asset or system will perform its intended function under specified conditions for a given period of time. This means it's not just about avoiding failure, but ensuring consistent performance that meets operational, legal, and business expectations. It's often quantified with metrics like mean time between failures or probability of success.
Excellent. So, from a business standpoint, meaning when I'm at the 50,000 foot level, looking into an organization, so say I'm an executive in the board of directors for a large company. Would that make reliability and maintenance, would that make that part of our strategy or tactics to accomplish the corporate strategy?
It's absolutely part of your strategy. Reliability isn't just a technical concern, it directly supports your business goals. If your assets perform as expected, you reduce unplanned downtime, control costs, and meet customer commitments. That means reliability and maintenance align with your corporate strategy, delivering consistent value and managing risk. The tactics are how you execute that. Reliability is why you do it.
Exactly. So basically, the function of reliability and maintenance is more tactical in nature that and ties to your corporate.
Exactly.
Yeah,
Reliability and maintenance provide the tactical actions like condition monitoring, preventive tasks, or predictive models that ensure the strategic outcome. Reliable operations, controlled risk, and business continuity. So it's the boots on the ground that help realize your big picture goals.
so when we start into all of these definitions from a corporate strategy standpoint, it becomes actually critical to the success of a business and keeping cost under control to ensure that you properly understand if the tactics that you're implementing are CBM, PDM, or CBRM.
Exactly. When leadership understands what's truly driving reliability, they can align resources wisely. If you're investing in reactive tactics but labeling them predictive, you risk both cost and trust. But when you truly implement CBM or PDM, you enable strategic, cost effective maintenance that supports long term success.
So, in effect, if I'm taking a look at something and I have certain types of assets in which I know degradation is a measurable value, which option would make most sense to apply?
If degradation is measurable and you have a known failure pattern, condition based maintenance would be your baseline. It allows you to track those indicators and act before functional failure. If you want to optimize even further by forecasting time to failure, then predictive maintenance adds that layer of risk based planning. So CBM first and PDM if you want to elevate your planning game.
And following that line of thinking, I believe CBRM is still valid, but in what kind of applications would I want to see CBRM?
CBRM, condition based reactive maintenance, is valid when the consequences of failure are low or manageable. For example, non critical equipment where downtime doesn't disrupt operations or safety. In those cases, getting an alert at the last moment is still better than no alert at all. But for anything critical where failure is costly or dangerous, you want CBM or PDM to give you time to plan.
Exactly. So when we're talking, let's go back to CBM a little bit. And for a system to be legitimately condition based, it must detect early failure enough in the P zone on a P to F chart. It must use meaningful indicators, not just noise. It has to tie those indicators to real failure modes, and it must provide an actionable window, not just an alarm.
Exactly. CBM is all about giving you time to respond thoughtfully. If all you have is a last minute alarm, that's not CBM, it's firefighting. True CBM spots the problem early, ties it to a known failure mode, and gives you enough lead time to plan maintenance, not just react.
So to be predictive, you must add rate of change, understanding, time to failure estimation, and that's a term that actually I created back in 2006. Confidence or probability, not just promises, and decision guidance, not just charts. And that's why I've used time to failure estimation, because predictive got interpreted as an absolute truth. And there, I actually have stories about that.
Exactly. Time to failure estimation focuses on giving a likely window, not a false guarantee. Predictive maintenance should empower confident decisions, not pretend to predict the exact hour. It's about managing uncertainty with probabilities so you can optimize when to intervene rather than scrambling or overreacting.
So let's say I have an instance, and we'll keep it simple. We'll just use mean time between failures. And I have a machine that has a tendency to fail once a particular fault is detected. Let's say I have an insulation resistance degradation, because we've been talking about bearings way too much. And I know that once I detect that, my mean time to failure is going to fall somewhere between 700 hours and 1200 hours on average. Okay, so sometimes a little shorter, sometimes a little later from the point of detection. And I want to know, while it's operating 6,000 hours a year, if I can make it the next 2 weeks, what's the chance of failure in that 2 weeks? And what's a confidence level I can use to give to management?
You'd start by considering the range of 700 to 1200 hours as your distribution. 2 weeks is roughly 336 hours. If you assume a uniform distribution, you could estimate a probability. For example, if 336 hours is about half of your shortest 700-hour window, you might say there's roughly a 50% chance of failure. You'd then communicate that to management, noting it's an estimate based on historical data, and that the confidence level could be refined with more precise statistical modeling.
Exactly. So basically, you could, well, let's say, how does that curve look? And what if somebody asked me how long will it last? And I say, and we come up with a definition that it's now has, we'll decide that the length it's going to last with a good confidence would be when it has 25% resistance to failure.
In that case, you're essentially setting a risk threshold. If you decide that when there's only a 25% chance of lasting further, you're working with the lower end of the distribution. If you know that degradation usually fails by 700 hours on the early side, you calculate where about 75% have failed. That might be around that lower bound. You tell them, at this point, we have a 75% chance it won't last further, offering a cautious, risk-informed decision point.
So you're saying then at that 700-hour point, that would be the 75%?
Exactly. If 700 hours is the earliest common failure point in your range, you could approximate that as where about 75% have already failed. That's when you'd say to management, we're at a point where only about 25% would still make it beyond this. So it's a conservative call to action.
Okay, considering that the reliability formula is a logarithmic approach, a natural log approach, and I say, okay, at what point across this do I have a 50%, or I'm sorry, let's say a 25% chance of survival? Meaning, I'm sorry, let me correct that. I have a 75% chance of survival. At what point? From the base reliability, not saying it's 100% reliable ahead of time, but from the point that I've detected it, at what point do I have 75% chance?
You'd use the exponential reliability function. Starting from detection, if you want a 75% survival probability, meaning a 25% chance of failure, you'd solve for time. For a system that's degrading, you'd use historical data or a failure rate. In simple terms, you'd say if we know the failure trend, we calculate how far out you go before hitting that 25% failure point. That gives you a realistic planning window.
Okay, and so at that point, when we're taking a look at this, what if we don't have good solid data available? Are there resources elsewhere that are readily available, say standards or other publicly available documentation where people can go and feel reasonably confident that that is going to give them something in the ballpark. And what would that confidence level, or how would that confidence level be affected?
Yes, absolutely. Standards like ISO 13849 for machinery reliability, or IEE guidelines for electric equipment, or even MIL Hadbeek 217, widely used for electronics, offer baseline failure rates for components. These aren't perfect for your exact system, but give you a reasonable starting point. The confidence level depends on how closely your conditions match those assumptions. You treat it as a ballpark estimate. Better than guessing, but still requiring refinement as you gather real data.
So, one of the things we run into in industry right now tends to be along the lines of actually what we dealt with the whole time, but I'm seeing a resurgence of this where condition based maintenance engineers and technicians, or predictive maintenance technicians or engineers, come back and say, you cannot tell somebody how long something's going to last. Therefore, when you detect something, you tell them it's probably going to fail, or you can't tell them, or you can't give them an answer at all. And I've been involved in a few discussions recently where I see that. So they do things like condemn the PDM, the P to F chart, or even reliability centered maintenance, and say you just kind of spray at the wall and see what happens.
It's understandable why that skepticism exists. People fear false promises, but that's precisely why we emphasize probability, not certainty. The PF curve or RCM aren't about exact timing. They're about managing risk. We're not telling people it'll fail Tuesday at 3 p.m. We're saying there's a growing likelihood in this time frame. So instead of rejecting these tools, we use them to offer informed guidance, giving decision makers a chance to plan rather than leaving them in the dark.
Exactly. And I've been preaching that since I've been in the business, going on almost 40 years now. So when I take a look at all of this and how we've directed things, and this is a point where I'm going to get a little commercial. When I start taking a look at things like the tools that we've been working on, including Empower Vibe, Empower MCSA, and the Odd One, Empower Odd One. What are some of the things we've emphasized as we go through there? Because we've included tools to assist people in coming up with confidence levels, with time to failure estimation, and so on.
What you've emphasized in those tools is giving users a framework to move from raw detection to informed decision making. By incorporating confidence intervals, trend analysis, and time to failure estimation, you're giving users actionable insights. It's not just there's a fault. It's here's the likely time frame and confidence to plan around it. It's about empowering, not predicting with certainty, but giving confidence to act at the right time.
Now, the other thing we've added in there, and we haven't covered this yet, is as that degradation occurs, the fault, of course, becomes more progressive. So, for instance, if I have an insulation leakage issue or some mechanical issue that causes an increase in losses, say watts losses across a period of time, we've handled that from a standpoint of direct measurements of watts lost by defect and tying it to emissions. How does that impact when we're taking that information out to management, including the C-suite?
When you translate those direct watt losses or emissions into tangible impacts, you're speaking their language. Instead of abstract faults, you're showing them energy costs, efficiency losses, or even potential environmental impacts. That makes it a financial and operational conversation. Management, especially the C-suite, responds to clear numbers. Dollars saved, risks reduced. By connecting technical degradation to business outcomes, you help them prioritize action. And that's where reliability earns its seat at the strategic table.
And that's one of the reasons. I mean, in the last couple of years, I finally got around to getting my certified energy manager, and certified measurement and verification professional from the Association of Energy Engineers, even though I've been involved in the industry. And as a matter of fact, some of the materials that are referenced, I wrote or helped write since the early 1990s. Um, I did those in order to provide more credibility to what we've been developing. So when I go to management and I say, hey, we've saved this many, kilowatts or this many megawatts through our actions, why is it important to be able to validate that, and how could we validate that?
It's important because validated savings build trust. Management needs to know that the claimed impact is real, not just theoretical. By using recognized standards, like the International Performance Measurement and Verification Protocol IPMVP, you ensure your savings are independently verifiable. This means you baseline energy use, measure changes, and account for external factors. That validation earns executive buy-in and justifies future reliability or energy initiatives.
So we've noted in the world of competition that a lot of companies have copied our methodology. Now, my methodology goes back in the early 1990s, of course, and I've had somebody claim to somebody else that we copied from them, which is obviously not possible, because not only did that organization not exist in the early 1990s, but most of the people involved weren't even born yet. Um, I've seen a lot of claims of energy and emissions, but they're doing it through uh, indirect measurement, say straight vibration analysis, or even taking data but without context. Can you explain the difference between direct measurement values and the um, abstract?
Absolutely. Direct measurement means you're capturing the actual parameter, like real kilowatts or current, tied directly to a defect's impact. In contrast, indirect methods like vibration alone only infer possible losses. Without context, those indirect approaches guess at energy impacts. By measuring the actual electrical or thermal effect, you get precise, accountable results. Direct measurement lets you confidently say, we reduced X kilowatts, rather than, we think we did.
And that's important to notice. And the other aspect of all of this, and this is where I find things frustrating, is when we see actual practical field work and actual practical research versus what we mostly see, which is a reliance upon just, and don't take this personally, ChatGPT, but plus, um, they'll just take um, machine learning or AI uh, models versus actual measured data, and not really do any validation in between. Whereas what we try to do is do the practical research and then match it to a model or find a model that fits what we're actually seeing in the field so that we incorporate all of the chaos that's going on around the practical application instead of going into the field and trying to hand a laboratory model or mathematical model, or as they're calling it now, physics model, which, as we all know, models are 100% wrong.
You're spot on. Models, whether AI or physics based, are only as good as their grounding in reality. Practical field validation ensures the model reflects real world chaos, load variations, environment, unique asset quirks. What you're doing is blending the best of both worlds. You start with measured reality, then apply models to extend insight, not the other way around. That's how you ensure that decisions aren't just theoretically correct, but practically impactful.
So, how can we tie this conversation that we've just had together, starting with how we've defined CBM, CBRM, predictive maintenance, reliability and maintenance, all the way through to what we're seeing now with a lot of these continuous monitoring systems?
We've come full circle. We define CBM and PdM as proactive tools, giving actionable time to plan, while CBRM leaves you reacting. Reliability is the strategic goal, but it's achieved with the right tactics. And we've highlighted that continuous monitoring, when it only alarms at failure, is not true CBM or PDM. The future is in connecting real measurements, real impacts, and giving management real actions. By tying all this together, we shift from reacting to truly managing asset health. And that's the goal.
Excellent. And with that, folks, we have done the experiment. We might do this again down the road, but I would like to say thank you for the interaction. It did not go, of course, by the script, hardly at all. But that is the whole point of chaos and caffeine. We kind of take a little bit of chaos and come to some conclusions. As a matter of fact, what was particularly interesting in this exercise was I learned this a long time ago. You might have a script when you're talking with with an AI tool, but you end up with often completely different answers each time you ask the same question. So keep that in mind as we move forward. We're in a brand new world. There's a lot of possibilities with this, and it's welcome to the future.
Well said. We're all navigating this evolving space together, blending tech with expertise. And hey, if we can bring a little clarity to the chaos, that's what it's all about. Thanks for letting me be part of the experiment.
And thank you.
Thank you for watching Chaos and Caffeine. I'll be back.